Hello, once again I welcome you all to MSP lecture series on transmetal chemistry. In my previous lecture I was discussing about the classification of ligands. Under that I was discussing about the ligands with hydrogen as donor atom. Okay, let me continue from where I had stopped. I gave different methods of preparation of metal to hydrogen bonds and also to make metal to H2 bond where H2 acts as a neutral ligand, and also I showed you how a neutral ligand such as H2 initially binds through sigma and then eventually with excess of electrons when they move from metal to sigma star of hydrogen, a HH bond breaks and then that leads to the formation of two MH bonds. So, let me continue giving preparation of some more compounds with the different transition metals. Now, let us look into oxidative addition method used in the formation of metal to hydrogen bonds. So, this is a square planar iridium 1 complex, this is also called as Vasca's compound. So, when you add H2 here, there will be concerted addition happens, oxidative addition, that leads to the formation of an octahedral complex, 18 electron complex having coordination number 6 with the 2 MH bonds, 2 iridium to hydrogen bonds. One can also make, as I mentioned, I will be elaborating this reaction later, keeping both thermodynamic and kinetic aspects to see how this reaction is reversible. I would give you more information about this reaction. Now, let us see what are the other methods we have to make metal to hydrogen bond. Another important method is sigma bond metathesis. Let me take one example here. A NMO bidentate ligand and having this group here. So, dimethyl phenyl methylsilane, when you add H2 to this, it forms a dimeric compound having 2 bridging hydrogen bonds. A symmetric molecule of this type is formed. So, that means there is some similarities there between the formation of metal to hydrogen bonds from H2 and also the formation of metal to carbon bond from olefins. For example, it forms something like this initially, and one can also show something like this. This represents 3 bond concerted oxidative addition. This will be in equilibrium and then can split into 2 H bonds. And then if you take, say for example, tungsten complex of your olefin, okay, or we can make it very general here. Okay. Now, this can also be in equilibrium with something like this. Or if we take acetylene, something like this. Okay, these are the few comparison I have made with olefins binding and its properties, and of course here also how a triple bond being a pi can also change through back bonding to pi star of these olefins is more or less very similar to what happens in case of the interaction between H2 and M. So, there the back bonding happens to sigma star in case of hydrogen, whereas in this case it is pi star. So, now let us look into more examples. Besides utilizing metal to hydrogen bond for hydrogenation reaction, is there any possibility of exploring other organic reactions? There are plenty of them are there. It is not just MH bond formation is only good for hydrogenation of unsaturated molecules, but it can go beyond, and it plays a significant role in many organic reactions. Let me start writing a few such reactions to make you familiar with the importance of MH bond. Just let us consider one MH bond, let us not worry about what other ligands we have. Okay. So, we will start with what would happen. I will keep on writing several reactions here. So, what would happen if I add oxygen to it? If I add oxygen, oxygen can be inserted between H and M bond to form something like this, or if I take CO, CO can also be get inserted something like this, and of course with later with appropriate reagents one can take away this CHO group, okay, into the right kind of substrate if you use. Then what would happen if I take CH2NH2? So, in this case one can get MCH3 bond, and then ammonia NH3 can come out, and probably it may bind if vacant position is there on metal center. If we take a olefin such as ethylene, then the insertion takes place here to form this type of compound. This is addition reaction happens here. Then if we take, say for example, a fluorinated ethylene, is the same thing. So, here also one can get H. So, this entire fragment is inserted between MH bond. These are all insertion reactions. If we take acetylene, you can do these things. Apart from these, there are several other reactions. Let me write a few more reactions. If you take H6 here, it forms an interesting compound of this type. If we take this cation, then again this whole fragment is inserted between MH bond to give a species of this type. If you take an azide, organic azide, If you take isocyanide, some more examples I am going to show you. Let us take carbon disulfide. Okay, this is very important. It can form if we take CO2, lot of groups are working on reduction of carbon dioxide. If you take this one, it forms these are some of the important reactions, and by knowing these reactions, probably if you want to look how these reactions happens, you should be able to use in several other organic transformation from this point of view, and especially this carbon dioxide insertion is very important from the point of looking into easily available carbon source and how effectively or efficiently we can convert using cheaper metals carbon dioxide into useful organic molecules. From that point of view, some of these reactions I showed is very important, and there is enormous potential in using MH bond for various organic transformations. With this, so let me stop discussion on hydrogen donor ligands. Now I shall move on to ligands having carbon as donor atom. Of course, you know that when we talk about carbon as donor atom, we have an entire new domain is there in front of us, that is organometallic chemistry. This organometallic chemistry deals entirely with formation and reactivity and then structure and bonding and all aspects related to metal to carbon bond. Nevertheless, since I am doing classification of ligands, I shall talk little bit about what are the carbon donor ligands we have, how one can make these complexes, and also how we can use these compounds in some applications such as homogeneous catalysis. So now let us come to this should have been lecture 30, however let me continue in this lecture, and then probably in lecture number 30 also I will be continuing further talking about carbon donor ligand. When we talk about carbon donor ligands, some of these molecules or fragments will come into the picture. So alkyl, all alkyl, whether you take CH3, C2H5 or anything for that matter, and aryl are carbon donor ligands. Besides that, we have neutral ligands such as carbon monoxide and carbon thiomonoxide. But as I mentioned earlier, this is not freely available and we cannot isolate this one in pure form. Nevertheless, we can convert some sources of CS and use it in situ to generate a CS to metal bond, and then carbon dioxide, very important, carbon disulfide and N-heterocyclic carbenes, Fischer carbenes and a range of olefins and alkynes, all these are essentially carbon donor ligands. And as I mentioned, a systematic study of all these ligands and more constitute what we call it as organometallic chemistry. But nevertheless, here also let us look into the reactivity and some chemistry related to carbon donor atoms briefly, and this is called fullerene C60 molecule. You know that this one can treat with amines to do addition reaction, very similar to what we do with isolated olefins. Okay, one can, for example, you treat with ammonia, you can get amines, you can make this way. And here when we talk about carbon, we come across two type of carbenes here, and this is a Fischer carbene. Fischer carbene carbon is singlet state, that means lone pairs are there and it acts as a neutral ligand and it can even stabilize metal in zero valent state. And then metal always has some non-bonding electrons. These electrons can be taken to empty pi star orbital. That means these Fischer carbenes can also act as good sigma donors and good pi acceptors. And in this one Schrock, this is a triplet carbon we are talking about. So that means it essentially forms bonds with metals and sharing electrons like this, and of course when these two electrons goes, you will be having C2 minus, that means 4 electrons are there occupying 2 orbitals and they make here metal to carbon double bond, and mostly metals are in high valent state. and again this compound is widely used in many reactions, metathesis and other things. So, now Fischer carbene is the starting material for Wolff-Dodds reaction. What is that Wolff-Dodds reaction? Let me write here, it should be 2 dots should be there. For example, you take Fischer complex of chromium pentacarbonyl So, R prime can be hydrogen, in this case it is hydrogen. When you treat this one with an alkyne, substituted alkyne, so here we are using 3 carbon fragments. So, this is 4 and then this is R5. So, that we know the relative position of that one in the product. So, here in this case when you trade this one with an alkyne, one of the carbon monoxide comes out from chromium and then we get cyclization product. And then now this entire aromatic group binds to, and now you can see this is forming a eta 6 arene, I would say. This is an 18 electron complex because chromium is 0 valent state and 6 electrons are coming, 6 electrons we have and another 6 electrons. So, it forms an 18 electron species here. So, this reaction so called Wolff-Dodds reaction here, and that means Fischer carbene is the starting material for this kind of reactions. So, Schrock carbene is used in the synthesis of very important step-based reagent. So, what is step-based reagent and how it is formed? Let me write that to make you familiar with step-based reaction and also step-based reagent. We are considering here Cp2 . So, this one later I am going to write in this fashion, it is understood that is eta 5 here. So, I will be writing this entire moiety, for simplicity I will be writing it as Cp2Ti. So, when you treat this one with dimethyl aluminum chloride, one can also write in a dimeric state, then you have to take half equivalent of this one. Plus 1 molecule of comes out, and of course, you may be curious to know the structure of this one. Structure will be something like this. We have one methylene bridge is there and also one chloride bridge is there. So, this one readily detaches aluminum fragment to give plus here what you get is half equivalent of Al Cl dimer. So, this is called Tebbe reagent. So, for what purpose this Tebbe reagent is used? So, let us take this reagent. If you treat this one with a ketone, it forms, initially it forms a intermediate of this type, and then here what happens, Cp2 Ti, this comes out, and that leads to the formation of so this functions very similar to Wittig reagent. So this is where shock carbene used in the synthesis of tip base reagent, and tip base reagent looks like an alternate to Wittig's reagent. Okay. Let me stop at this juncture and continue in my next lecture discussing about ligands having carbon donor atoms.